Good afternoon, class. This is lesson 2, covering section 1.3 for our linear algebra class. Apologies for being a little late with this video. Most of these videos I'm going to start posting first thing in the morning. It's just these first couple days. I got some other things going on with my schedule. But the future videos should be posted much earlier in the day than what I've done today and yesterday. So apologies for that. Luckily, we're not too far in the class yet, so there hasn't been a lot due yet. Participation question 2 will be due tonight by midnight. Homework 1, so after this video, I'm going to go ahead and post information about homework 1. That will be covering some of the textbook exercises, and that will be due this coming Tuesday. I guess some words of advice for the homework. So the homework, it will be submitted handwritten on paper. So you look at the exercises on the textbook, and then you'll have to show your step-by-step work on your paper to get to your final answer. And then that will be submitted online to Canvas. So you can use a free app like CamScanner or something, so you can take pictures, upload it as a PDF, and then that'll be taken care of. Again, that should be posted, or homework 1, I'll post the information this afternoon, so you'll have that. And that'll be due this coming Tuesday. Right. With that being said, let's go ahead and get started for today's lecture. So we are looking at section 1.3, which is largely all about defining, 1, what it means to be a vector, and 2, how can we use vectors to construct everything else in our given space. So we've said before that these linear equations, they can exist in a 2-dimensional space, 3-dimensional, 4-dimensional, 5-dimensional, whatever size space you like. The larger space you have, then the more entries you're going to have in a given vector. So what does that actually look like? Well, if we're thinking about 2-dimensional, we know that an ordered pair such as 1, 2, this is an ordered pair. This can be something like this, right? And so we'd represent in the space. However, when we're talking about vectors and when we're talking about linear equations, we're never dealing with just a single instance of a point. Instead, we're dealing with either an equation which represents some line in our space. And in fact, a vector, we're also going to think of as some line in our space. What is a line then? Well, a line has to have some kind of direction. So this line then is always traveling out of the origin. In fact, vectors we're going to think of as being these arrows or lines that are projecting out of the origin. The point then, 1, 2, is going to be indicating, okay, where is the end of the arrowhead? Or in other words, this is telling us like how steep should our line be, right? This vector is then represented as a column vector, 1, 2. So we list the first the first coordinate first, and then the second coordinate of our ordered pair, and it's listed in this fashion. So we have this vector here, and with any vector, you can think of, if you're thinking from a physics background, you may think of a vector as being something that has a direction and a magnitude. Magnitude being how long the vector is. So I could have another vector, let's say 2, 4. Right? Now note the vector 2, 4 coming out of the origin has the same slope as the vector 1, 2, except this vector 2, 4 is longer. It's double the length. So this vector 2, 4 has double the magnitude of the vector 1, 2. But they are both traveling in the same direction. Now, for the sake of this course, since it's a linear algebra class, we're not so worried about the physics application per se. So we're not going to talk a lot about magnitude and stuff. It's not really important in this class. But the point I want to get across is, what is a vector? How do we represent it? And how can we visualize it in terms of a graph? So a vector is some line traveling out of the origin in some direction, and its magnitude or length is determined by the distance from the origin to that point, the end of the point, where the arrowhead is. Okay, good. Well, in fact, all of R2, so remember boldface R stands for the set of all possible real numbers. When I raise it to the second power, you can think of this as being R times R. In other words, it's any real number paired with any real number, right? So R2 is really just the set of all possible ordered pairs in the XY plane. Or put another way, we could say it is the set of all possible vectors, column vectors, such that X and Y are in R. In other words, X and Y are real number constants. So we can represent R2 in this way, and everything in R2 can be represented as some kind of vector. All right, so what can we do with vectors? Well, if we have a vector, let's say U equals 1, 2, and V equals, let's say, negative R2, according to what we have written here so far. And we also know from yesterday's lecture that when we're dealing with these linear equations, when we're dealing with matrices and now vectors, we're never going to be multiplying our variables because we want to stay with linear. We want to stay in the world of linear equations, linear functions. So we're never going to be multiplying two vectors together. But instead, what can we do? Well, in the linear sense, you can always add variables together. So we're going to have addition, which means we can do U plus V. Okay, well, what does that look like? When we're adding vectors together, we're quite literally just going to compare entries and add those corresponding entries together. 1 plus negative 2 is negative 1. 2 plus 3 is 5. And this is going to be a new vector in R2. So we can add two vectors together to create a new vector in our space. We can also apply scalar multiplication. So this is the only multiplication we're really going to have access to, at least for now. I can take some constant and say, well, what is 2 times u? Well, I'm taking 2, the constant, times the vector, 1, 2, and I'm going to get 2, 4. Which we already saw this earlier. The vector 2, 4 is double the vector 1, 2. So we can see the scalar multiplication work out this way, where when you have a constant times a vector, each entry is going to be multiplied by that constant. So things to note, at least when we're adding vectors, they have to be vectors from the same dimensional space. If I, for example, take a vector in R2, let's say 1, 1, and maybe I want to try to add it to a vector in R3, 1, 2, 3. Well, now I don't have a third entry for the first vector to compare to. I don't have a way of adding these two guys together because there's no entry here for me to add to 3. So these vectors cannot be added together. There's no way to do it. So in order to add vectors together, they have to be from the same dimensional space. Scalar multiplication can be applied to any size dimension vector. It's really this addition thing we have to worry about at this point. Okay. I'm going to take another drink of water before I erase that. Okay. So we know that we can multiply a scalar by a constant, make it bigger. We can make it longer. If we multiply it by a negative constant, which you can do, that's just going to flip the direction, right? If I take the vector 1, 1, and I multiply it by -2, well, now my new vector is -2, -2. Now, it's going to maintain the same slope. It's rather just going to flip the direction the arrow is going in. So my original vector, which was here at 1, 1, is now at -2, 2. So note between these two vectors, the scalar of this vector, it's still on the same line, right? When I take the scalar of a vector, it's still on this same line. I'm rather just changing where it exists on the line. Is it stretching in this direction, or is it stretching in the opposite direction? So I can also multiply it by a negative and flip the direction. Okay, so we can scale vectors. We can add vectors to create new vectors. And in fact, we have a special name for this in linear algebra. This is called a linear combination. What makes it linear? Well, the fact that we are only adding vectors and scaling them. We're not doing anything else. We're not multiplying vectors or anything else or raising them to powers. This allows us to call it a linear combination. So in general, if we have let u1, u2, u3, up. So remember this subscript notation. I'm just using the subscript to indicate which u am I talking about. Let u1 through up be vectors in R to the n. Now, in this definition, I haven't specified what dimension this is. This is just dimension n. So each of these vectors have n entries, right? u1 has, it has something in the first position, something in the second position, ... It has n entries in its column vector because it is in Rn. Okay, so P and N are two different constants. P and N are not necessarily equal. P is telling us how many vectors am I looking at. N is telling me what dimension are my vectors in. How many entries do I have for that vector, right? All right, C1, C2, ... CP be constant scalars. These are just constant real numbers. They're not vectors, just constant real numbers. Then we're going to say, then y is also in Rn. Y is some new vector in Rn, so it's a vector with n entries, where y equals C1 times u1 plus C2 u2 plus ... CP up. So I'm taking a linear combination of these vectors, u1 through up. I'm adding them together with some scalars. Who knows what these scalars are? But when I scale them and add them together, I can get some new vector y. So y is a linear combination of u1, u2, u3, ... up. So this gives us some new kinds of questions we can ask. We can think about, like, okay, here are some vectors. Here's some other vector. I would like to know, is it possible for some other vector to be a combination of other vectors I already have? And we'll look at examples of this in just a moment. Okay, So this is what it means for a vector to be a linear combination of some other vectors. It means there is some way to multiply them by some scalars and add them together to result in this other vector. That's what it means to be a linear combination. And we're going to find out as we progress that being a linear combination of some other vectors is actually a very special property that we're going to dissect more, honestly, pretty much through the end of the class. This is going to be a very important property, so you want to make sure you understand what we're talking about here. Okay, so let's see some examples. In particular, let's say u1 is the vector 1, 0, and u2 is vector 0, 1. Okay, so I can imagine if I'm thinking in the R2 space, here's my vector u1, that's in the x-axis direction. And here's my vector u2 in the y-axis direction, right? So I have these vectors that are exactly 1 unit long. They have a magnitude of 1. One is going in the horizontal axis direction. One is going in the vertical axis direction. Well, in fact, any vector you like can be created as some combination of these two guys. As we continue in the class, we're going to find out there's something special about these two vectors in particular. And in fact, in R3, R4, R5, any size dimension space, we're going to find there are similar vectors that are very important to those spaces. But in particular, you can imagine with me that, well, what if, for example, the vector 2, 3? How can I get to do 2, 3 as a combination of u1 and u2? Well, the vector 2, 3 equals 2 times 1, 0 plus 3 times 0, 1. So in fact, this new vector 2, 3 is a linear combination of u1 and u2. So if I call this new vector v, v is a linear combination, I'm going to abbreviate here, is a linear combination of u1 and u2. Okay, great. So this is what it means to be a linear combination. But more specifically, these two vectors in particular are very special in that no matter what vector you imagine, any vector you imagine is a vector, or in R2, we're just talking about vectors in the two-dimensional space. Any vector in R2 looks like this. It's some x, some y. X could be anything. Y could be any real number, right? But no matter what x and y are, that's really just x times 1, 0 plus y times 0, 1. So in fact, every vector in R2 is a linear combination of u1 and u2. Why is that happening? What's special about u1 and u2 to make this happen? These are details we're going to talk about more in the coming, or probably next week. But I want to go ahead and just whet your appetite. So you got this idea rolling around the back of your head. Right. So I've given you an example of a vector which is a linear combination of other vectors. But what if we don't know if a vector is a combination yet? How do we find out if a vector is a linear combination? So let's look at that next. Let's suppose I have a vector, a1, and now we'll talk about in R3. I have a vector 1, -2, -3. Oh, I'm sorry. That is a -5. Sorry. I'm looking at the lecture notes for section 1.3 that are on Canvas. That is a -5. Let's say A2 is another vector, and A2 is going to be the vector 2, 5, 6. And let's say B is a third vector, 7, 4, -3. Okay. And we would like to know, is B a linear combination of A1 and A2? Now, I also want to take a moment to highlight that in these examples I'm doing here in this lecture, I'm just taking linear combinations of two vectors. But as we saw in our definition that we provided earlier, you can take a linear combination of 3 vectors, 4 vectors, 5 vectors, 6 vectors, so on and so forth. It doesn't just have to be a linear combination of 2. I'm just using 2 here in this example for the sake of simplicity. Okay. So what is the question we're trying to answer? We want to know do constants, some unknown constants, I don't know what combination of A1 and A2 would result in B. So I want to know what constants x1, x2, do constants x1 and x2 exist such that x1 times A1 plus x2 times A2 equals B. This is the question we're trying to answer. If B is a linear combination, then that means there's some way to scale A1 and A2 by some constants that if I multiply them by constants and vector B. We want to know, is this possible? Okay, so how do we solve this? Well, really what we're boiling down to is we're trying to find out, does an x1 and x2 exist that can make this happen? Well, we can rewrite this as x1, the information here that we already have. X1 and x2 are unknowns. Maybe a solution doesn't exist. That's possible. Maybe B is not a combination. Maybe no solution exists, but we don't know yet. All right, this is the answer. This is the question we're trying to answer. But I could multiply x1, I could multiply x2, and then I can add these vectors together. So really what we're trying to do is, if I multiply this vector by x1, I'm going to add it, then we end up with this. In other words, lo and behold, what do we have here? Well, this question is the same thing as asking, does a solution exist for this system of linear equations? I have one equation equal to 7, a second equation equal to 4, a third equation equal to -3. This is a system of linear equations, which we already know from yesterday's class. We can turn this into an augmented matrix. Right? We can rewrite this as an augmented matrix. And so we have 1, 2, 7, -2, 5, 4, -5, 6, -3. Right? We now have this in the augmented matrix format for this system of linear equations. And now we're just trying to find out, okay, well, what's x1? What's x2? So on and so forth. That could make all of these equations happy at the same time. It's possible there could be more than one solution. Or it's possible there are no solutions, or maybe there's just one, just as we discussed yesterday. So, all right, I'm going to erase part of this. I'm going to leave the augmented matrix since that's what we need. And I'm going to leave this up here, I'm going to erase what we've done here so far. Okay. So we've seen from yesterday that one way to solve this kind of thing is to row reduce it. If I can get it into reduced echelon form, then it's going to tell us the answer. So we have, I want to get this into reduced echelon form. So now we're going to do that step by step here. And firstly, we can note that, okay, I would like to get a pivot in around the 1 for the column corresponding with x1. So, okay, next, to be a pivot, though, I need all zeros below the pivot. So I need to get rid of this -2 and -5 in row 2 and row 3. So first, I'm going to write out what I'm modifying. I want to modify row 2. How do I modify row 2? Well, I want to add 2 times row 1 to it. I'm going to use this row that I'm going to have my pivot in to get rid of the other entries. But while I'm doing that, because this reduction here is only going to change row 2. It's not going to change anything else. But just for the sake of space and for the sake of time, I can do 2 row reductions at the same time. I also want to modify row 3, and I want to change row 3 by adding 5 times row 1. So I'll have 5 times 1 added. It'll give me a 0 in that entry for the third row. So I can do both of these at the same time. That's okay. In fact, it'll save space and time. Row 1 is not changing. For row 2, I'm taking 2 times row 1 and adding. 1 times 2 is 2. When I add, I get 0. 2 times 2 is 4. When I add, I get 9. 7 times 2 is 14. When I add, I get 18. That's my new row 2. Okay. I've got my pivot nicely stated there so far. Now what's my new row 3? I'm taking 5 times row 1 and adding it to row 3. 1 times 5 is 5. When I add, I get 0. 2 times 5 is 10. When I add, I'm going to get 17. 5 times 7 is 35. 32. Oh, wait, hold on. Did I add this correctly? 5 times 2 is 10, plus 6 is 16, not 17. Right, I believe that's correct now. Yes, good. Okay. Now, in its current format, I would like to get a pivot here next. I'd like a pivot in the second column. Ideally, I'd like to try to get a pivot for each variable if possible. I have 2 columns with variables or that correspond with variables. And so I want to try to get a pivot in each one of those. If I can't, that's okay. It just means I have a free variable there. We'll see what happens. So now, in order to make this 9 a pivot, I need to get 0 below it. Well, if I try to think about reducing this, I'm going to have to multiply 9 by some weird, nasty fraction to add it together to get rid of this 16 here. But instead of doing that, let's save myself the hassle. Instead, remember that these rows, again, are just equations, right? If you have numbers in common for a given row, you could just factor them out, right? Remember, row 2 here is really just the equation 9x2 equals 18. Well, if I divide the equation by 9, that's really the same thing as saying x2 equals 2, right? So in other words, what can I do here? I can modify row 2 by, I'm just going to divide it by 9. Let me simplify the numbers here. Let me turn this pivot into a 1, which I want for reduced echelon form anyways. I want to turn this pivot into a 1, so I'm going to divide the row by 9. And you know what? While I'm at it, I see for 13, I have 16 and 32. We can go ahead and divide row 3 by 16, just so that we don't have these really big numbers to deal with. So our new matrix will be 1, 2, 7, 0, 1, 2, 0, 1, 2. And now it's much nicer to deal with, much more manageable. I'm going to reduce, I'm going to do 2 more reductions, then we'll be all done. So first of all, I want to get zeros below the pivot for this 1 here. So I need to modify row 3. I'm going to take row 3 and subtract row 2 from it. But at the same time, to get into reduced row 1, by taking row 1 and subtracting 2 times row 2. And notice, by using row 2 with this pivot to get rid of the 2, it's not going to change the pivot I already have up here because I have a 0. So if you used pivot locations to change the other rows above and below, it's not going to mess up the previous pivots you've already created. So that'll be a key kind of step when you're doing these kind of things. If you've kind of taken this class before, or maybe you've heard about it before, this methodology for getting to the reduced echelon form is also called the Gauss-Jordan elimination. It's just a more fancy formal name for this row reduction we're doing. So you can use that to look it up if you'd like to learn more about it. This is called Gauss-Jordan elimination. This is a methodology for elimination. Did I spell that right? Elimination. Are there 2 I's there? I'm having a brain fart. Yeah, I spelled it correct. That's elimination. Okay. Gauss-Jordan elimination. This is a methodology for row reduction. I don't think it's super important that I go over all those specific steps and have you memorize them. I think rather it's just more intuitive if you can get used to the idea of like, okay, let me just go 1 column at a time. I'd like to get a pivot in the top position if I can, and then continue from there. Right, so we have these 2 row operations we're doing last. So first, I'm going to modify row 1. I'm taking row 1 and subtracting 2 times row 2. So nothing changes with my first pivot. 2 minus times row 2. 2 times 2 is 4. 7 minus 4 is 3. Row 2 is not changing here. And then row 3, I'm taking row 3 and subtracting row 2 from it. Well, lo and behold, we get all zeros. This is a good sign. A row of all zeros is perfectly fine. A row of all zeros just means that equation wasn't important. We didn't need it, right? And it's still consistent because there is no pivot in the equals column, right? There's no pivot in the equals column, and so this is a consistent system. It has a solution, but we can also see that, oh, there's no free variables, right? Each variable, x1 and x2, have a pivot. So there's no free variables. So there is only one solution that exists for this problem. What is it? Well, the first row as an equation says x1 equals 3, x2 equals 2. This is then our answer. And we can double check, does this make sense? The whole thing we're trying to do is we're trying to determine, is there some way to add A1 to A2 so that we get B as a result? Well, this says if I take 3 times A1, okay, so 3 times 1 is 3, plus 2 times A2, well, 2 times 2 is 4, All right, well, 4 plus 3, that'll give me the 7. Great. 3 times negative 2 is a negative 6. Plus 2 times 5 is 10. Well, negative 6 plus 10 gives me the positive 4. That's good. Negative 5 times 3 is negative 15. Plus 2 times 6 is 12. Well, negative 15 plus 12 gives me negative 3. So lo and behold, B is a linear combination of A1 and A2. Not only is it a linear combination, but it is exactly this combination. And there is no other way to combine A1 and add them together. If we had a free variable, there could be multiple solutions, but we didn't get a free variable here. Okay, good. Let's see. I would like to also give an example where we do have a free variable. So let me pull that up real quick. Let's see, we need the textbook. Bear with me for one moment. I had to download the textbook again. And here we go. Okay, we are in chapter 1. We're looking at 1.3, trying to determine if different vectors are linear combinations or not. Okay. See, I'm trying to see if they got a good example here. Oh, they don't here. Okay. Well, we're going to talk more about free variables as we continue in chapter 1. I've kind of hinted at them a little bit, and I kind of gave you a definition for free variables in yesterday's lecture. But we're going to hold off on really seeing examples where they pop up just yet, because we want to really make sure that we get a grasp for how we're solving these kind of problems first. And then we'll talk more about these other cases when, well, what if we have infinitely many solutions? What does that look like? How can we tell? Actually, I lost track of time. I did, because I know the video I posted yesterday ran a little bit long. I didn't mean to make it that long. So I was aiming to try to make today's video a little bit shorter. But let me just go ahead and close with, let's look at today's participation question. This is participation day 2. So if you go on Canvas, participation day 2 was published this morning. Okay. So in participation day 2, there's a question asking about how many pivots does a coefficient matrix have. So I'm just going to write that matrix here on the board. Oops. My marker is dying on me. Let's see. Do I have another marker? I do. Okay, here's a different marker. There we go. So here we have a matrix 1, 2, 3, 4, 0, 0, 0, 6, 0, 7, 8, 9, 0, 0, 0, 10. All right, so where do we have pivots? So remember, when we were talking about echelon form and reduced echelon form, pivots are referring to the leading entry of each row, and you can only have one pivot per column Because a pivot must have all zeros below it. A pivot does not necessarily have to have all zeros above it. That's only for reduced echelon form. But just in echelon form, a pivot must have zeros all below it. So I'm just going to look at, okay, row 1. It looks like I have a leading entry here, all zeros below it. So great, that meets the criteria. That is a pivot. Okay, great. Next, I can look at row 2. And okay, I've got a 6 here. So in the current form of this matrix, 6 is not a pivot. However, could it be argued like, well, could I reduce this matrix further? Could I use 6 to get rid of this 9 and 10? Sure, you could do that. Then it would turn into a pivot. However, we don't really need to do that. We're just looking at, in its current state for this matrix, is 6 a pivot? No, because we don't have all zeros below it. Okay, so I'm now going to look at row 3. Here's 7. And it has all zeros below it. Great. This is then a pivot. Another way to think about pivots is that you can go one column at a time, because ideally, remember, each column is going to correspond with a variable. So really, we don't care if there's a pivot for every row. What we really care about is, can we get a pivot for every variable? Can we get a pivot for every column? So we got a pivot for x1, pivot for x2. We look at x3 and, well, there's nothing here, right? I can't use 3 because it's not the leading entry. I can't use 8. It's not the leading entry. And I have zeros for the other 2 rows. So there is no pivot in x3. x3 in this current form is free. Okay. Then what about x4? Well, we already know 6 is not a pivot because I don't have zeros below it. But 10 is a pivot. So for pivots, the question states this is a coefficient matrix. So partly what that means is, if I were to ask the question, is this matrix consistent or is it inconsistent? The answer would be neither. There is no equals column. It's not an augmented matrix. We can't say anything at all about whether a solution exists because there's no equals column. There's no equal sign. x1, x2, x3, x4, these are just variables, but we have no idea what they're supposed to be equal to. So this matrix is not consistent, and it is not inconsistent. Those vocabulary terms do not apply to this kind of matrix. All we can say about it is that we have 3 pivots. Even though we have a pivot in the last column, that does not tell us this matrix is inconsistent because it's not an augmented matrix. Because it's a coefficient matrix, we can't say anything else about this matrix. All we can say is there are 3 pivots. All right, so that's the answer for today's participation question. That covers the lecture material for section 1.3. Of course, if you have other questions, concerns, by all means, please reach out to me, email me. Office hours will begin next week, starting on Tuesday. And if you're looking for any additional help or tutoring, the Math Learning Center also offers online tutoring. If you look in the syllabus, you can see the link I've left there for information about the Math Learning Center. So you can also get tutoring through there online. They're open anytime, Monday through Friday, 11 to 5. You don't have to sign up or anything. You just show up whenever you like, and there will be somebody in that Zoom link who will be able to help you. Okay, that's all for today. Best of luck. Let me know if you have questions, and I will see you all tomorrow.